in 1780, Pierre-Simon de Laplace, this is from the Lake Observatory archives, this is his great book of celestial mechanics. I can't pronounce the French, Traité de la mécanique céleste. And within this book, he identified a curious behavior that Saturn and Jupiter undergo. Jupiter goes around the sun almost 5 times for every 2 times that Saturn goes around the sun. It's not exact. It doesn't average out to 5 to 2, but it's relatively close. And so in the mathematical framework that he wrote down, what this means, and if, those of you who know about series expansions will know that generally the terms in a series expansion get smaller and smaller and smaller. And that's what it looks like is happening in the solar system series expansion. It looks like the terms get smaller and smaller, but there's one that's quite a ways down that happens to be quite large because it has a very small denominator. Just happens to be that way. And that term is responsible for Jupiter and Saturn undergoing this oscillation of a period of several thousand years. And when Laplace realized that, he was able to add that to his theory of the motion, which already explained the really long-term variations, and he was able to get a very precise prediction, both for where Saturn will be in the future, but also more appropriately or more importantly for where Saturn was in the past. We have observations that were made by the Chaldeans, which were transmitted through Ptolemy, through the ancient Greeks, which go back more than 2,000 years. And there was a particular observation that said that at a particular time, and this was synced up to eclipses, so we know exactly when it was, and Laplace knew exactly where it was, a star, Gamma Virginis, was observed to be 2 fingers from Saturn at this particular time. And if you take just plain old Kepler's law and run the solar system backwards, Saturn is nowhere near that spot at that particular time in the sky. But if you take Laplace's theory and run Saturn back, it's exactly there. And so it was this dramatic prediction in the sense of where Saturn was and dramatically confirmed. And Laplace was enormously proud of his accomplishment. Laplace was pretty well connected. He had an audience with Napoleon after Napoleon came to power. And Napoleon fancied himself sort of a mathematician. He liked to do things like, if you ground up the Great Pyramids and build a wall around France, it would be 12 feet high, and that he liked those kinds of calculations. And so Laplace showed Napoleon, these calculations and explained the great inequality, and he explained how this is all unfolding like clockwork. And probably because Napoleon didn't really understand what he was talking about, Napoleon said, "And who is the author of all this?" And what he meant by that is like, who's the divine providence who's actually doing the work, who's actually making this framework that you can study? And Laplace raised himself up to his full, I'm kind of embroidering this here, but Laplace raised himself up to this full height, and he said, "Sir, I have no need for that hypothesis." And what he was talking about there was that he had no need for a benign deity to step in and alter either the courses of the planets or the courses of human affairs. And he has this very interesting quote, put both the French here and the English, because this is a very important quote. And what he's saying here, if you read it, is that if you understood where all the particles in the universe are at a given moment, and you understood which directions they were going at that particular moment, and you use the law of physics, then you can make a prediction for what will happen from this point forward. And if you can do that, there's a number of things quite interesting that come into play. For instance, free will does not exist. All the particles inside your head and all of your interactions are predetermined by the laws of physics, and it's all just going to unfold, and if you could do a perfect calculation in Laplace's view, then you could know the future. Right? So this is known as Laplacian determinism, and this extreme confidence in the ability of the laws of physics in science itself to sort of really allow you to be all-knowing is a very extreme stance to take. And in a sense, it's very interesting. It's completely opposite from Newton's stance. Newton's stance was doing this sort of thing exceeds the force of any human mind. Clearly, God is coming in and rearranging things. Clearly, we're actors on a stage that God is in charge of. Whereas Laplace, in studying exactly the same problem, namely the motion of the solar system planets, he came to the exact opposite conclusion. Now, as the 1800s went on, observations became better and better. So one of the favorite things that 19th century astronomers did was they made very, very accurate measurements of where the planets were as a function of time. And the telescopes got better. Micrometer sights came into use. The optics of the Fraunhofer refractors were excellent. And so you could very, very, very nicely get sort of ephemerides for the solar system. And Urbain Gégé Leverrier, who was the discoverer of Neptune, looked at this problem of marching the planets forward in time, and he realized that Laplace's solution was only approximate. He wrote that Laplace's calculations cannot be used for an indefinite period of time. What he's saying here is that the framework that Laplace set up is good for a few tens of thousands of years, perhaps a few hundreds of thousands of years, but it won't work for the duration. There's other terms further down the series that must be important, and those small deviations were becoming apparent with these extraordinarily accurate calculations that were made by Leverrier. Now, Leverrier was a scientist of, it's sort of Einstein and Carl Sagan rolled into one. He had a public profile, and he had an extraordinary analytic facility. And he was extraordinarily famous at that time because he had dramatically predicted the discovery of Neptune. He had looked at the perturbations of Uranus's motion, and he had realized that there was a trans-Uranian planet. He had used Newton's laws of gravity to predict where in the sky that would be found, and it was indeed found within days of his issuing his prediction. So this was something that was just astonishing to the public in the 1840s. And so when Leverrier said that his fellow Frenchman, Laplace's calculations were perhaps not good, and that the problem of the stability of the solar system was still there, it was a big deal. It was a big deal enough so that King Oscar II of Sweden had to know the answer. And he said, I'm going to give 3,000 gold crowns and a gold medal to the first person who can predict, who can prove either that the solar system is stable or that it is not stable. And so there was all sorts of entries, all sorts of excitement about this. And turned out that the contest kind of came to a somewhat unpleasant end because Henry Poincaré showed that the problem is impossible to answer even if there's just 2 planets, let alone the 8 that were known at that time. If there are only 2 planets going around a star, then there is no way to predict for all time what will happen. He showed that mathematically. It kind of just let the air out of the tires of that contest. They ended up giving him the prize. One reason why they gave him the prize was because the judges weren't quite up to understanding what he had done. And so it's interesting now to look at a related but simpler problem. Okay, so the story that I've told is one that you can look up, and read about in various places. I'm kind of hewing to a well-trod path. Now what I'm going to do is I'm going to get off this path and show some things that you haven't seen, or that some of you haven't seen. So around the time when Poincaré made his discovery and won the contest about the stability of the solar system, there was a German mathematician completely unrelated. And this German mathematician made sort of an odd statement. He said that let's take a a mass of mass 3, a mass of mass 4, and a mass of mass 5. And let's place those three masses, perfect point masses, at the vertices of a 3, 4, 5 right triangle. And we'll do this in such a way that the mass 5 is opposite the length 5, the mass 4 is opposite the length 4, and the mass 3 is opposite the length 3. We set them down at rest in space and ask what happens. So you can use Newton's laws of gravity to determine what will happen, but it gets rather difficult. What's clear is that the bodies will fall in toward each other, and then something will happen. And this mathematician, Meisel, he stated, it's a bit like Fermat's last theorem, except that it turns out not to be right. He stated that the motion will be periodic. And what he meant by that was that the three bodies will do something, and they'll come back exactly to where they started, and then they will do it again and again. And so 100 years ago, a scientist in Kiel in Germany decided to take this up. And he used, you can't get an analytic solution. You can't do this with pencil and paper. The only way to do it is to compute it. And so he used something that was probably similar to an adding machine or a cash register, an old adding machine type calculator, to do a numerical computation. And he tried to find out what would happen, but he was unable to get anywhere with it. This is the last page of his paper, and he's basically pointing out in German that it's just not clear what's going on, and it's not clear why the mathematician Meisel said that the solution would be periodic. There's no evidence of that. And so this is what the starting condition looks like. So this is just the first part of a calculation that I did, in which you have the three bodies, and they're sort of have just started moving, and so they're heading towards each other. This is the body of mass 5. That red one right there is the body of mass 3, and this is the body of mass 4. And we can kind of look and see what happens. This is as far as they got 100 years ago using effectively the cash register. What they found was that body 3 starts falling, bodies 4 and 5 fall in, they fall around each other. They sort of make a close encounter. And then body 3 falls through here, has an encounter with body 4, and is headed off in this direction. And that's when they gave up. It was just too much work. And so we can kind of watch what happens. And here we go. So this animation, I think, is going to take, oh yeah, I can sort of give you a quick overview. So what's going on here is I'm just computing the motion and plotting it. And in addition to plotting where the particles are, I'm also plotting the instantaneous force vector to sort of show which direction they're being pulled. And so you can see as time goes on, there's a succession of encounters between the bodies. So right there, bodies 3 and 5 had an encounter, and now bodies 4 and 5 are going to have an encounter. And they kind of go back and forth in this intricate dance. And the dance goes on. And what I'm showing here is basically the sum of the total motion on a logarithmic scale. And so each time there's a peak here, that corresponds to an encounter between two of the bodies. Now, this goes on for like 4 minutes, so what I'm going to do is I'm just going to sort of scrub through and try to show it faster. So as I do that, you can see that they kind of go back and forth. Interestingly enough, right here at 69, time 69, they almost come back to exactly where they started. They almost do, but they don't quite. You let them go, they do their thing, keep doing their thing, and then rather dramatically, at the very end, body 3 gets ejected. So you can see it leaving right there. And bodies 4 and 5 head off together forever. Body 3 heads off in one direction after this complicated dance. And so Meisel was wrong. He was incorrect. It's not a periodic solution. It resolves itself into a binary pair heading in one direction and 3-body heading off in the other direction. But this problem, which sort of came about at the same time that Poincaré did his work, has some very interesting features. And one of those features is that if you make a very, very small change in the initial conditions for the bodies, that is, if you, instead of starting them perfectly from a 3, 4, 5 right triangle, you just move body 5 by 1 part in a million away from where it started. If you do that, then starts off, as far as you can tell, exactly the same. They fall in. Eventually, what you see is that the solutions start to diverge. So there's a faint gray line here, which I plotted, which shows what happens if you make it just a tiny initial perturbation. The system starts out doing exactly the same thing, but then it diverges, and eventually it becomes completely different. Turns out that if you make an absolutely very, very small change to the initial position of body 5, you can actually get it to be perfectly periodic. Instead of coming almost back to where they started, they come exactly back to where they started. And tiny changes start out the same, but then they magnify and they grow larger and larger and larger. And what happens, and this is what Poincaré showed in his mathematical proof, in his elegant mathematical proof, is that if you have this phenomena, then you cannot make a prediction that's good for all time. All that you can do is make a statistical statement about what will happen, and you can make a prediction that lasts for some amount of time before becoming invalid. And so this is really perhaps one of the greatest realizations that we as a species have had about how nature works. This sensitive dependence on initial conditions, the fact that nonlinear equations do interesting things, is a very profound result, and it affects every facet of what we do. The great this was realized again in the 1960s in the context of the weather. And there's this sort of statement that a flutter of a butterfly's wings in Brazil will cause a tornado to visit a certain part of Texas. And in a sense, that's completely true, in the sense that if I swirl my hand around and change the air currents in this room, if I come back 3 weeks from now, the weather patterns all across the globe will look completely different than they would have looked had I not done that. It sounds like, just some sort of just trying to exaggerate, but it's actually true. The weather behaves like this simple Pythagorean system in the sense that it's sensitively dependent on initial conditions. And so the question becomes then, how far in advance can you predict the weather? And what can you say beyond that? So, here's a picture from the GEOS 14 satellite. This is actually Hurricane Sandy about to slam into the Northeast. And so, the question is, and it's a question of huge value to us, how far in advance can we predict the weather? Anyone know? I heard about a week. So I heard a week, and a week is about right. I was interested in this myself, and so this is a plot of how many days in advance we can predict the weather to a useful degree of approximation. This was made by the National Weather Service. National Weather Service has some extraordinary computer programs and computers which are continuously running models. And so what they do is, as they improve the models, they also keep the old models running, and they compare the new programs with the old programs. And as a result of computer power increasing, and as a result of initial conditions being better known, our ability to predict the weather, not my ability, but us as a species, our ability to predict the weather has gotten better and better. So now, in 2011, we now can predict the weather to a useful degree about 8 days out. So an interesting question is what determines how far out we can predict the weather? If we have the 3, 4, 5 right triangle, and those are masses, measured in grams and distances measured in centimeters, then it takes about an hour for the 3 masses to come together. The first infall takes about an hour. And our ability to predict the future in that system lasts for a few tens of hours at the most before the sensitive initial conditions kind of takes over. So there's something to do with the dynamical time of the system, namely the time it takes to make kind of one crossing, and the amount of crossings that we can predict into the future, which is best a few dozen or less. So with the weather, the relevant quantity is the rate at which sound travels across the globe. A jet airplane, a commercial jet, is flying a little bit slower than the speed of sound. Take roughly 24 hours to fly around the globe in a commercial jet if you don't have to stop to refuel. And so what that means is that if we know what the weather looks like now, then we have a very good approximation of what the weather will look like sort of one system time later, which is roughly a day. The sound crossing time for going all the way around the Earth is roughly a day. And so some number like 10, 5, a dozen days into the future is how far we can predict the weather. And that number of dynamical times depends very strongly on the system. Clearly, for the solar system, the stability of the solar system, we have no problem predicting where the Earth is going to be next year, 10 years from now, or 1,000 years from now. What's the effective dynamical time there? So what I thought I would do is, before talking about the solar system, I'm talking about another system that people are interested in and try to do predictions for. And that's the stock market.